Juan Moreno is the Principal Technology Evangelist for Quantum Technologies at AWS. So he's in a pretty good vantage point to tell us about what is going to happen with the quantum cloud. Thanks, Juan.
Thank you. Oh, I'm pointing to myself. I was talking to Atul before my talk and say, hey man, are you going to talk about superposition and entanglement? No, don't worry. No, I'm not covering any of that. So it's like, thank you. So now I have to figure out how I'm going to talk about those things. I will cover a few theoretical concepts, but Atul covered part of the things that I wanted to say, so I'm not going to just confuse you with another angle of looking at things. I work with the quantum networks engineering team in AWS. So basically what we do is to explore the space in quantum networks. And quantum networks, as you heard before, there are many applications of it. And the one that I'm the most interested on is to create and distribute keys for encryption. That's how in AWS we mostly understand quantum networks and the first useful use case. That's my LinkedIn. If you want to add me, I'm interested on that because I'm interested on cooperating, on doing demos and POCs where we can show the world that this technology works. Hopefully I will convince you of that. It's not like quantum computing that is still being developed. These things actually, you can buy them and you can install them like switches and routers, and it does work. So I'm interested on showing that to the world. That's what the part of the evangelist part is about. Let everyone know. I have a small agenda, but it's very loose. So I expect to be interrupted with questions if something is not clear.
So I have a question.
There you go.
So have you solved the secure key distribution problem?
Within certain boundary conditions that I will explain.
Okay.
Within certain boundary conditions, yes. What I really want to give you is tips and clues on to make your own judgment when you read articles. Again, as Atul was mentioning, in media, sometimes you see things that you don't know if it's actually a breakthrough as it is announced. Sometimes it's not. Sometimes it's the real thing. So hopefully I will give you tools to make your own opinion about it. But the key piece is about, I want your help to see how can we address the challenges of implementing quantum key distribution in the cloud and at the scale that we need. So I will explain to you what the problem is, and I'm hoping I can get some ideas from you. And hopefully I will have time for a couple of implementations. This is a field where academy and industry are cooperating very close together. I was mentioning to someone earlier that usually industry goes behind. The academic research goes first and they do the big discoveries, and then we think it's cool and we try to implement it in real life. So that's usually how it goes. But I have a couple of examples where those things are put in practice. I have a lot more that I put in the slides. If we don't have time to cover, I will make them available for you to check later. Superposition. So I was just planning to explain what that is. I'm not going to cover it again, but you got the difference from quantum computing. That is the most popular field in quantum technologies. We have quantum computing, quantum networking, and quantum sensing. That's usually the three fields that we have. I'm going to be focusing on quantum networking and specifically quantum key distribution. And my qubit that we were talking about is going to be a photon. And you see lots of them over there, and this is how we're going to basically be distributing keys. Space is an okay medium to distribute keys between 2 points. We use fibers because they are convenient and they are already implemented, but space is totally okay. As you can see there's two options. The bit, the classical bit, I represented it with two dots. It can be only in one state. It's either 0 or 1. You have a transistor that if it has passing electricity through it, you get a 1. If there's no electricity, you get a 0. And then you have millions, billions, trillions of them in our phones and devices to do calculations. In quantum computing, we have the quantum bit. In my case, it's going to be a photon. You can map into 0 and 1, that's as you see there, but it can be in the quantum networks, we like orientation and polarization, the same as in your glasses when you hit the sun. You deviate the light so it doesn't hit your eyes. It's the same idea. So I can say that my two states are diagonal and horizontal, for example. When I am in superposition, I'm in some probabilistic mixture of both states. One thing that I'm going to give you as the first tip when you read articles in the media, if you start reading something and it says, it's 0 and 1 at the same time, warning alert. Whatever you read afterwards, it might be all hype and not entirely true. So no, it's not two states at the same time. It's just some probabilistic combination of both. And those alpha and beta that you see there, it can be negative probabilities. It can be complex numbers. So don't think about it in a deterministic way, like 30% of this and 70% of that. Okay. So that's for superposition. Enough. On the right-hand side, you see nodes, quantum nodes, and the green lines are channels, right? We are basically trying to build a network with this. What I'm going to be interested on is to send in my photons. And as I said before, it can be fiber, it can be open space, because photons make for very good qubits to travel in this medium. So in this simple network, I can prepare a photon to be in superposition of these two states and send it to another location. And when that's traveling, if I have anyone spying on my channel, I'm going to be able to detect immediately if they read the result. Because when I read a particle that is in superposition, the wave function collapses and becomes a particle, and then it becomes a 0 or a 1 or horizontal or diagonal, whatever that was. And the other side that was waiting to receive the message over there, if we start from here, will know immediately that the state has changed. So that's the basis to do good cryptography and building from there. Entanglement means that we get two of these qubits correlated together, and we take advantage of that correlation to do a lot more powerful things. Atul covered almost all the things that you can do with entanglement in his talk. Implicitly was mentioning about it. When two particles are entangled, they are correlated. So when I read the state of one, I will know without even looking at it what the state of the other one is going to be in the measurement. And that's going to allow me to basically do things or transport states at distance. And states can mean data at distance. Ideally, I want to have an advanced network, like this one that I represented here, where any 2 points in my network are entangled with each other. And the main difference here is that if you imagine that those dots are quantum computers, just to go back to the quantum computing example, if I have two quantum computers here linked by a classical link, they can work together, and I have two quantum computers working together. But if I manage to build a quantum channel like between these 2 points with entanglement, then I have exponential power on those quantum computers. Basically, I will have 2 to the power of the number of qubits all together that I managed to link together. That's extremely difficult to do. And for my use case of key distribution, it's not something that is used often. For the moment, I just care about superposition, prepare my photons, and send them across to create a string of random bits that I'm going to use to create a quantum key that I'm going to use to encrypt my data. So many measurements, and I will get 1, 0, 0, 1, 1, 1, 0. And that's going to be a truly random stream that I can use for encryption. The point, we have more Alices and more Bobs. You're going to get a lot of that in this field. We want to make Alice and Bob to talk to each other. And we have several elements here. This is the general picture where we have the encryption algorithm that is represented with that symbol. That is public, and it's being constantly stress tested by the cryptographic community. This is the thing that everyone is trying to break all the time in order to make it more secure.
Juan, how fragile is the encrypted key going across that public channel?
Fragile. You have several mechanisms. There are protocols built. It's not just us sending ones like this, but you have a reconciliation process, discarding all the noise, and make sure that the final key that you build is a fraction of all the photons that you set across. So there are protocols that exist to distill a good key. BB84 is the most common one. My encryption key is going to be truly random, and it's going to be exactly the same on both sides in Alice and Bob. And then the blue square is going to be my safety zone, where everything can be in clear open text, and I can see the data. That's safe. I don't need to worry about security in that space.
Are you only looking at symmetric encryption?
For quantum, yes, but I'm going to combine it with asymmetric encryption, as you are going to see in a second. I will combine both. Then we have the public channel that we are going to call it if, because we have our eavesdropper always looking there, and we consider it unsecure by default. We are going to be constantly having attempts to steal our data there. And that's an assumption in all the security proofs. So before we go into the quantum part and how photons travel across and we make this happen and why it's secure, let's see different methods to distribute information first of all. I can send my key with a physical person. This is not fiction. This is actually niche use cases where highly secure cases, government, military things that require an extreme security that cannot rely at all on digital methods, still being used, the person with the suitcase going with the key from one place to another. Obviously, the problem with this is that it's very hard to scale. You cannot send an email to your friend and send someone with the key for him to decrypt information. It defeats the purpose, right? So what we do is to do a mathematical wrap around the key, and that is what is called public key cryptography. Basically, we have to build a very difficult to resolve algorithm that is very easy for the receptor to decode, but it's very difficult for an attacker to crack using brute force. Things like Diffie-Hellman and RSA have been using in the internet since I was born, so now you know my age. And recently, we have started to see more adoption of what they call post-quantum cryptography. Second tool or second tip for you. Post-quantum cryptography has nothing to do with quantum. Post-quantum cryptography, there you go, is another mathematical method where we are making that algorithm a lot more complex that not even someone with unlimited computational power will be able to break. I'm not going to say unlimited, but someone like with a quantum computer, for example, will not be able to crack, as far as we know today. So it's a lot stronger mechanism that instead of factorization of numbers, for example, like can be one of the previous one, you will use factorization of polynomials or other complicated things. So Kyber is the most popular, already standardized PQC algorithm, and it's increasing adoption these days. But we haven't talked about quantum yet. Now, going back to the beginning and the concepts that we cover, the third method in which we can send the key from Alice to Bob is using the properties of quantum mechanics. We are going to need a special channel that we were discussing in the previous talk, the quantum channel, that is going to be basically sending the photons encoded in the key, and we're going to partition that key and use it to encrypt our data. The good thing about this method is that there's nothing to crack. There is no math involved. If I try to read the key, Bob immediately knows that I was trying to do so because, as I said before, the wave function collapses, and we change the quantum state of the particle. So we will detect that attempt immediately. And quantum key distribution is there are several protocols within quantum key distribution to make that happen. So what do we do? Well, you get the best of both worlds if we can. What we want to do is to try to another different use of defense in depth that we have seen today in another talk in a different context. But here we use it to illustrate the fact that we could use the traditional mechanism that we have been using since the 70s. That in this case, I put there Diffie-Hellman. And then we could put another layer, or to be precise, concatenate my key with a post-quantum cryptography protocol, and then have a third encryption mechanism with QKD. So if an attacker comes and reads my data, tries to break my key, they will need to break 3 lines of security. And in page 21 and 22 of the report that was distributed before by Jim, you can read more about that, actually. In page 22, actually. Cool. Okay, so what's next? I think we covered the basics with this. Well, when we have the key, we have just put it on our endpoints to protect the data. All right.
I have a question, sorry. I might be misunderstanding this, but if somebody tries to read the key, does that mean that the intended recipient of the message can no longer read the message?
No, you will discard that key. You will need to rotate or refresh the key to resend the message with a new key.
So you have to send the message again?
You need to send the
With a new
message
key.
again. Or depending on how you build your logic, you might just drop QKD if it was an attempt to attack QKD, and you still can use your other 2 mechanisms. Those are independent of an attacker trying to break your key. The key will get delivered anyway. If I try to do brute force in post-quantum cryptography, I can start doing it, and the communication is still uninterrupted. That will not stop the communication to happen. It's only when I use a QKD key or a quantum key when the attack is detected and the key gets dropped.
Okay, but doesn't that kind of, I mean, I guess I'm having trouble seeing how it's useful, because just the attempt to intercept that message can prevent you from receiving that message and force you to have another message sent.
You need to build a
So
logic
you're
around
denying
it.
service.
You are technically right. You can create a DOS attack by trying to read the key all the time, but you need to build your logic around that. You need to have a mechanism to detect when it's an attacker, and you need to do, as things stand today, a good hybrid approach with these 3 methodologies. So if you get a constant attack in a channel that you cannot detect where your attacker is, fall back to just post-quantum cryptography and traditional cryptography combined together, which is still give you 2 layers.
Okay, thanks.
And a question on your timeline. Not too long ago, the Office of Management and Budget issued a report that said how to protect against, how to basically start protecting. And their estimate for the time frame of a quantum computer able to essentially crack cryptography was anywhere from 2026 to about 2030. Would you agree with that? You're nodding.
Yeah, I'm familiar with that one. It was for RSA, and they said it's going to be 20 years, and it was...
No, this is a report that just came out, and they said that basically that blue on there, the year that that's going to happen is somewhere between 2026 and 2030. So in the next 2 to 6 years.
Oh, 2 to 6 years.
Yeah.
I wasn't aware of that.
Yeah,
report.
that's their prediction. I was wondering if you were like...
It seems ambitious in the state of the technology, but it's all about coming up with a smart algorithm to break existing security. But this is cipher suites that have been running for 48 years. So I'm not saying it's not possible, but...
Can I do a follow-up on the previous question here?
Sure, please.
My assumption, and which could be wrong, is that you're using the quantum channel to actually deliver the key to each end. And then once you have the keys at each end, you use those keys to encrypt the messages.
That's right.
And an attack on the channel wouldn't be attacking the key, it would be attacking the messages. So
The key that has already been delivered can be used, and there's no problem with the key once it has been generated. It
Right.
becomes classical.
that's what I was trying to get to, yeah. So
So it's the distribution that we are protecting here. Maybe I wasn't clear on that before. So the green line, what we are protecting is the creation and distribution to the key, to the endpoints. Once the key is created and is being used, and it has been considered as good from the quantum point of view, it gets used normally.
What, help me a little bit with RSA encryption, where the real value was key length, public-private. Help me here with the advantage of this over that methodology.
Do you mean in terms of computational resources that are needed to?
No, I was thinking more of the degree of protection. The one key is public, one key, is not. You still have to distribute those keys.
Right.
It's like this method looks like we're only dealing with one key as opposed to.
Right, it's
Is that
symmetric.
the main thing?
It's completely symmetric, and the thing is that you are protected by quantum mechanics. The source of how that key is created didn't depend on an algorithm. So you really don't care too much. Well, it's not that you don't care, but if it gets detected, there's no brute force attack to do because there's no math.
RSA was about key distribution, right? You use your public key to deliver the private key, use your private key to deliver the public key, and in open space. So
You could do that. Technically, it's possible. The NIST does not recommend to do so. But you could do that.
but that's why it's susceptible to quantum computing, because you can calculate and break that code.
Right.
If you've got symmetrical keys, it's transferring them to the endpoints that's the risk. Once they're in the endpoint, you're in that blue box.
Once you consider them safe at that point, they are safe. Exactly. Yeah.
If you add a whole bunch of noise to the public-private key pair, then you're protecting that transmission.
Right. Yes, but that's again math, right?
It's math, yes.
Yeah. Cool. I love that.
I had a
Yes.
question. I wanted to go back to the conversation around attempts to read the key.
Yep.
And then if you detect an attempt, you start all over again. Do you have any statistics around how feasible it is, or how often people who attempt actually can see the key?
We don't have enough data yet. There is literally a handful of vendors that are building QKD boxes that you can buy commercially, and everyone that is in this space is testing them intensively now, including us. But there's not an official report at the moment or some post-mortem analysis of existing attacks or things like that we have to answer your question.
Right. So the thought is that if you get the idea that somebody even tries, assume they're successful and they're going to start all over again.
That's right. You drop the key immediately. And actually, the noise of the channel is considered an attack. It's not going to be perfect. When I'm synchronizing photons across, sometimes it's not going to be correct. Alice and Bob are not going to read the same thing. When they don't read the same thing, I prepare a horizontal, and Bob says, I'm seeing that you prepare a diagonal polarization. Let's drop that. Next, you are really shooting photons in these devices very fast. And sorry, I lost the point of your question, but we don't have enough data for the attack.
I guess the point of my question is, do you have any? You're protecting against something that you have no idea how successful it is going to.
Right, you are only making assumptions. We have covered assumptions a lot of times these days. You are assuming that if there is a certain percentage of noise in the channel, that's an attack, and you are dropping. And after a certain percentage of errors, you completely drop the connection or completely drop that key because you consider that it's not safe anymore. You need to set up your device to say, this is just noise and it's tolerable, versus at this point the noise is too much and probably someone is eavesdropping on my channel. That's how you do it.
Is there a distance and a latency in the quantum channel? Is there maximum distance? Does it?
Yeah, I'm going for it.
Okay.
That's the main problem. That's what I want your help with. I'm going to fly through Harvest now, Decrypt later, because we don't have too much time. But basically, it's important to start encrypting as soon as possible because the data that we are storing today could be decrypted in the future. And for things that needs to be on the shelf for a long time, that really matters, right? Like medical records and things like that. Distance limitation. 150 kilometers. It used to be 100 kilometers 6 months or 9 months ago. Now the vendors are getting better. Sorry that I use kilometers. All the papers and usually use the system of kilometers. I got used in my head to it, and I'm Spanish as well, so I'm more familiar with it. We have the channel. This time I just put a straight line. And at this time I turn Alice and Bob into an AWS region. I'm going to explain what that is. But basically the cloud on one side. And on the other side, we have someone, an office, enterprise, or a research entity trying to use QKD.
So, excuse me, over here, because I can't remember right versus left even when I'm done.
Almost the middle.
So I'm trying to take what I know about quantum communication and distances and things like that and map it to what you're saying. So is it the Chinese are doing this over satellite relays. I know 20 years ago we were able to do it over significant longer distances than that. Is that just is this something specific about the key part, or is this just any quantum communication?
Very good question. Two things of what you mentioned. We're able to do it at much longer distances. Number one, if we are just sending photons without hoping to build enough of them in each side to build a key, yeah, we can go farther than that. Or number two, you are using trusted relays to pass the key in many jumps. I'm going to try to cover that as well. Yeah, so we have this challenge that the quantum channel is not going to be able to cover more than 150 kilometers. And I love this example of the laser point. It's a different frequency, but it's the same. I'm shooting very far. If I go 150 kilometers from here, you probably will not see anything on that wall because the light scatters and disperses. It's exactly the same thing. It's just in a different wavelength, but it's the same. And yeah, I need to figure out solutions for that. So the colocation facilities, the data centers with both the cloud vendor, don't think on AWS, but any cloud vendor. I don't want to make this about AWS because I believe that every hyperscaler has the same issue. We need to put something in the middle to address the distance and also to protect the most important links that go outside of the facilities of that theoretical customer. What we do is to use defense in depth in a different way. We still use the classical encryption mechanisms, both the ones that we know since ever, plus PQC, to build an end-to-end tunnel. We could be over layer 3 with IPsec. We could even do layer 2 with MACsec. There are many things in the OSI stack that we could use with this traditional technology. And then we cover the most critical link. That is the one that goes, where am I? Here. The one that goes outside of the enterprise or the lab that wants to connect to the cloud, to a colocation facility where we share a space at a more reasonable distance. And I'm going to show you in the next slide that we have a bunch of these colocation facilities around the world that are usually closer to our customers and a reasonable distance to the cloud to close that gap. With this solution, what we achieve is, in general terms, a quantum-resistant solution. Another keyword for you when you read about this. Breakthrough. Quantum resistance has been achieved. OK, what of that is quantum? Let's see. Let's evaluate that. So this is a quantum-resistant solution because it's resistant to the attack of a potential quantum computer trying to break your key, but for different reasons. Here is math-based. Here is quantum-based. So let's take a look to that region. I have covered all this part, but why we are not putting QKD boxes over here and basically making the connection quantum safe end-to-end. There is ways to pass keys from one every 150 kilometers if we want to. But it's a tough problem. Sorry. This is how a region looks like. There's many of them around the world. And what I'm depicting here is 3 availability zones, that those AZ1 to 3, that basically are built for resiliency for customers. And then inside every availability zone, you will have at least 2 or 3 data center buildings. Sometimes there is a lot more. But basically, there is a natural disaster that takes the whole data center down, or there's a power outage or something like that. If you build your application correctly, you will be resilient to failures on these things. Now, I want to implement QKD here. And the reasonables usually are, the distance usually are reasonable in terms of 150 kilometers reference that we have. I could protect those links. So if I have to start here, I'm not going to protect with QKD every single link inside my data center from every switch. Remember the blue box that I mentioned before? A data center will be considered as the blue box. I don't need to implement quantum technologies where I have a million layers of security to get inside. So it will be for those links that go outside. That can be, someone can dig a tunnel and grab my link and do something with it. That's where I want to protect. So here I will start probably with those things, those links. There are challenges here. These devices are not like the Cisco's, Junipers, and all these very mature devices that we're used to. There is, as I said, 5 or 6 of them that are really good, but not as good as just you can leave them running and without any human intervention do their operation. You need to build a lot of operational layers on top, and they need a lot of attention. So to build this in production, a company like AWS cannot go and say, yeah, we put 3 devices, Alice, Bob, from here to here, there. This region is now quantum safe. That wouldn't be serious. But the biggest challenge is the scale. This is an ideal picture. It's rarely the case. When you go to one of these things and you zoom in, there is resiliency, there is alternative routes, there is a smart routing. There's many things that you could potentially need to cover in order to make it happen. So even if you get all the devices to make it, even if you build all the resiliency with several devices and all that, you still need to cover a lot. And then this is one region. There are 34 regions altogether at the moment in AWS, and other vendors are the same. How do we define regions? That's a different story. Some people put a wall in a data center, and they say that they have 2 regions, but I'm not going to get into that. And we have 108 availability zones as per a couple of days ago. So it will be a lot of devices to implement. We are exploring the space. We really want to make this happen. But my job is to work with partners, with customers that are outside on those colocation facilities and trying to build these end-to-end solutions that for the moment are quantum resistant. And selfishly speaking, I want to learn from their implementation challenges. When we are trying with them to build these quantum networks right to the edge of the cloud, we want to see what things they run into when they are trying to run their applications and configuring the network.
I have a question, and I think I know the answer to it, but if country A has a quantum key distribution system and something happens and it has to spill over to country B, is there a danger that country B can subpoena the keys that were originally belonged to country A?
What does subpoena mean?
Well, I'll come in and say, we want those keys.
It will depend how you, I'm going to touch on that very soon, because it will depend how you build your logic for that, and you could avoid it. This is an example from the academia in China, where they cover over 1,200 kilometers in the ground by doing trusted nodes. The trusted node is basically linking those Alice and Bob together with many QKD devices, one after the next. What you do is something that it was mentioned in one of the previous talks, using an exclusive OR operation between the 2 keys. So basically, you build a temporal key that it's impossible to decrypt for an attacker, even if it goes inside the trusted zone. So you can build this way, using this trusted relay over in the ground, they were able to go 1,200 kilometers. But it's just an experiment. You never put this in production. I would never implement this because it's a single point of failure for every single step, an operational burden in every single step. And what about the monitoring of all these devices and so on?
So question on that, when you say that you've got the relays going, you're actually, non-cloning would mean that each key is different for each segment. And
That is
that's what
right.
you're saying. It's like if one of these nodes goes out, you're
You break the chain.
okay.
Right.
But it's not the same key somehow magically getting cloned at the relay station.
Correct.
'Cause
And
it
creating
can't.
temporal, when doing one-time path operations in every jump. And at the end, I get the key that I got at the beginning. But that key is not being transmitted at any point in the intermediate steps, thanks to the OTP operation. But yeah, it's operationally not doable. But it was a good demonstration. In this experiment as well, is the second method to overcome the distance limitations was to use satellites. So instead of pointing, instead of pointing like this, you point like this to your satellite. You have the ground station, that is going to be the trusted relay. And once you pass the atmosphere of planet Earth, it's vacuum. So the laser can go up, and if it's a LEO satellite, a low Earth orbit satellite, it will be able to catch your photons, grab them all, and go to another continent, go from East Coast to West Coast, and drop it. That's theoretically all possible. It has been demonstrated. It's all cool. Now, we are talking about implementing this for all AWS customers, right? It's a different story. And answering your question, John, is about how you build resiliency about that. We have been working with Verizon on doing a demonstration with 4 sites connecting to the cloud. And basically, we had to build 4 layers of complexity to make sure that we are not only creating keys and sending them around, but we have a buffer in case we run out of keys for whatever reason or the device goes down. Then we need a management layer that do routing of keys. If I'm in this area and I run out of keys with this element, but over there someone is communicating and they have plenty of keys, I need to find a way to request the keys to be able to serve this part of the network. So routing quantum keys as well, it's important. And this is what all these different layers are doing here. In that graph, I wasn't planning to include it, but I'm glad that I did. You see how one of the devices fails, and the time it takes to the management layer to redistribute keys and replenish again the buffer so you don't interrupt the service. If on top of that you put classical encryption, then you are covered. But it's a lot of work. As you can see, just for 4 nodes, it takes all this. So my question for you is, how do we scale this? How do we make it work better, right? I have more use cases, but I have nearly no time. So this is in Europe, in my hometown, actually. This is a network that uses software-defined networks to do something very similar to what I was explaining before. This is another cool use case that I haven't mentioned to you up until now. Quantum channel doesn't need to be a separate channel. It works better because it's clean fiber, dark and amplified, and it works better. But you could use the existing network of a telco provider and use a different channel and put your quantum channel there. It doesn't crosstalk. It works perfectly fine. Your key rate will be a little bit lower, but it totally works. And in this example, the local telco operator in Spain was willing to share the quantum channel with the classical channel that they use for their customers. And that was another demonstration that is still running. And I'm working with them to try to extend this to the cloud and build more use cases. That's what I have. Again, my QR code. And I have more examples that I will share with you if you want to read about them in other places in the world. Thank you.